things we know about matter is that it cannot coincide. What that means is that two objects, two particles, cannot be in the same place at the same time. But that is not at all true about waves. Waves can and do overlap. And when they overlap, they interfere. There are two types of interference. The first is called constructive interference. When two waves are in phase, when they're doing the same thing at the same time, at the same point, then those waves will add up and create a greater amplitude. This is, of course, easier to see with a transverse wave than a longitudinal wave. When two waves are completely 180 degrees out of phase, then you have destructive interference. They will cancel each other out, and you will get a reduction in amplitude. If they're the same size, you'll get complete destructive interference. And if the waves are partially in phase with each other, partially out of phase, then you'll get some constructive and some destructive interference. Now, this idea extends beyond waves that are the same wavelength and the same amplitude. You can have lots of different waves of various different shapes that overlap. And what you do is we use what's called the superposition principle. You just add up the amplitudes of the waves one at a time. And that's really how you handle interference. You can sometimes get complete destructive interference, sometimes you get constructive interference, sometimes you get a mix of the two, and that's pretty much it. Just add the waves up point by point, and you'll get yourself what the new resulting wave looks like. It is very common for us to take advantage of this. We can take waves and add more waves on top of them and add more waves on top of those and more waves on top of those and do that over and over and over again in order to get shapes of waves that you normally won't find in nature, like a square wave, which is close to perfectly square but not quite, or a triangular wave. These types of waves have very different sounds if they're a sound wave. Keep in mind that sound waves are not transverse, but we often will represent their amplitudes as something that looks transverse just because it's a lot easier to see, and that can confuse people. But if we have sound waves that are square waves versus triangular waves versus a regular sine wave, they really sound really rather different, as you can hear here. Here's a sine wave, here's a square wave, and here's a triangular wave. Big difference. They're all the same note, but a very different quality, or what we call timbre, to the sound. Sound waves that are of a slightly different frequency can add and subtract, can interfere in order to make what we call beats. You get destructive interference, which are very quiet, and then you get areas of constructive interference, which are quite loud. And so if I play two middle C, 256 hertz sound waves at the same time, they sound like one sound wave. But if I play a 256 hertz and a 257 hertz, you get that loud, quiet. That's called a beat. If I play 256 and 258, 256 and 259, 256 and 260, how about 256 and 270? 256 and 300. So it gets harder and harder to tell that those beat frequencies are there. They start to combine together and our ears just hear them as one noise when the two frequencies are too far apart. But when they're close together, you get a very, very pronounced constructive and destructive interference. And yeah, that means that loud plus more loud equals quiet. This is how noise canceling headphones work. They take the sound waves that are coming in and they flip them 180 degrees out of phase. Everywhere there's a compression, they put forth a rarefaction, and everywhere there's a rarefaction, they put in a compression, and they cancel each other out. But anyway, beats, you need to be able to calculate beat frequency, and it's crazy easy. Ready? Subtract the two frequencies. The beat frequency is just that. If you have 256 hertz and 260 hertz, the difference between those is 4. That means you're going to get 4 beats per second, like this. There you go. Those are beats. Another interesting phenomenon that we get with constructive interference is what we call a shock wave or a prow wave, or with sound, a sonic boom. You've seen these before easily. The wake of a boat. When a boat is moving through the water, it creates a crest. It pushes water out of the way, creates a crest. But if the boat is moving faster than the water waves, then the boat moves forward and pushes more water on top of it before the water had a chance to get out of the way. And then it moves forward and pushes more on top of that. So you get constructive interference that builds up like crazy to create a wake. The secret to not creating a wake is you have to drive your boat slower than the speed of water waves. Now, the same thing works with sound. If something is moving slower than the speed of sound, then you don't get that incredible amount of interference. If you do move faster than the speed of sound, then those sound waves, those compressions build up on each other like crazy, and you get what we call a sonic boom. Sonic booms are often misunderstood because a lot of people think that that happens the moment that the object breaks the speed of sound, but that's not true. A sonic boom is like the wake of a boat. It's a cone behind the object that is continuously happening the entire time it's traveling faster than the speed of sound. You just happen to hear it when that piece of the cone strikes your ears. So here in this brilliantly done drawing here, we have the guy who hasn't heard it yet, the guy who's in the process of hearing the sonic boom, and the guy who heard it a moment ago. Often enough, because things are moving faster than the speed of sound, these three people would hear it at what they perceive to be the same time, but there is actually a slight delay between them. This phenomenon actually even works with light. In nuclear reactors, when they first turned on some of the first reactors, they found that the water glowed blue. And the reason why is because the neutrons that were being created in the nuclear reactions were zooming through the water at not faster than the speed of light in a vacuum, that's impossible, but faster than the speed of light in water. Water has an index of refraction of 1.33. So take the speed of light in a vacuum, divide by 1.33, that's how fast light goes in water. These neutrons were going faster than that. And by doing so, they create an electromagnetic shock wave that creates a blue glow that we call Cherenkov radiation, named after Russian physicist Pavel Cherenkov, who won the Nobel Prize for explaining it in 1958. So whenever I hand a student a slinky and I say, hey, make a wave, they usually do something like this. And if you notice something, there's something interesting about what's going on here. Let's do that again. I take it, I'm barely moving my hand, but look what's happening to the slinky. It's vibrating higher and higher and higher. This is like when you're on a swing and a bunch of little pushes on a swing can build up to create a bigger and bigger and bigger sound. What's going on here? When I create that wave, I just create a little wave, and that wave goes down, it reflects off the other side. That reflection changes its phase. You see that? It starts as a crest, it comes back as a trough. Here's a better video of that. So it goes down as a crest, it comes back as a trough, and when it does so, well, it interferes with the next wave that's coming. And so you have waves that start to build up on each other and build up on each other and build up on each other. Now, so you have a wave traveling down, it hits the other side, and it comes back with its phase flipped 180 degrees. Obviously, a slinky or a rope or a string can't be in two places at once, and so they interfere with each other, and that interference creates a new wave. And isn't it interesting that a wave going that way, interfering with a wave going that way, creates something wave-like that looks like it's standing still? We call this a standing wave. In a standing wave, we call the points that are not moving. They don't just appear to not be moving, they're points that are actually not moving because of complete destructive interference. We call those nodes. A node is a place where things come together. So nodes of commerce were cities in the ancient world, right? Because where a bunch of people come together. So that's just what node means. And it looks like you have multiple ropes with a standing wave. You don't, but it looks like it. And it looks like they all come together on those points. Those points are nodes. The big parts where it's shaking with maximum constructive interference, those are called antinodes. And that confuses people like crazy because when they think anti, they think not. And so they say, okay, so the spot that's not moving is an antinode. Nope, wrong way around. Nodes are the spots that are not moving. Antinodes are the parts that are moving with maximum amplitude. And if you think about it, these standing waves can really only happen at a particular frequency or set of frequencies. If you shake too fast or too slow, then it's not going to work. Look at this lowest frequency standing wave. How many wavelengths do we have there? we have 1/2 of a wavelength. The next standing wave that we can create is, well, the ends have to be nodes. And so if we have the half a wavelength, the next thing we can fit and still have both ends be nodes is 2/2 of a wavelength. And then the next we could fit is 3/2 of a wavelength, and then 4/2 and 5/2 and 6/2. We have to go up as halves of a wavelength. So this lowest frequency, what we call the fundamental frequency, if we apply the speed equation to it, v equals f lambda, and then just solve, we get f equals v over lambda. Frequency equals velocity divided by wavelength. The wavelength of this thing is 2 times the length of the string, right? So the frequency is equal to the velocity over 2L. Those of you in AP Physics will need to know, well, what is that velocity? Velocity in a string or a rope is the square root of the tension over the linear density, the tension over the mass per unit length. And we can combine that together to get the equation for a standing wave's fundamental frequency. This is the lowest frequency you'd get off of, say, a guitar string, or the lowest frequency you can shake that slinky. So if we call that fundamental frequency the first harmonic, the second harmonic is 2/2 of a wavelength. So what is the frequency that goes along with that? It's got to be that same equation times 2. The third harmonic is that same equation times 3, and so forth. The 20,000th harmonic is that equation times 20,000. And so if we just represent the order of the harmonic, first, second, third, fourth, 20,000th, whatever, by the letter n, we end up with this equation for a standing wave that has a node on each end. Now, air columns are a little different. What is our fundamental frequency there? Well, in this case, anytime you have something with a closed end, that's where the liquid would be, the closed end has to be a node. It can't be maximum shaking there. And the open end is an antinode. So this could be a whistle or a flute or a trombone or any of those types of things. In this case, it just happens to be my beverage. So you have a forced node and forced antinode, which means how many wavelengths can you fit in it? Well, you can fit 1/4 of a wavelength with a node and then an antinode. What's the next number you can fit? 1/4 plus 1/2. And then 1/4 plus 2/2, 1/4 plus 3/2, and so forth. So going through that math again, the same thing we just did, you can get a very similar equation. This time you don't get v equals square root of f over mu. You get v is, well, the speed of sound, because that's what we're working with. And you end up with this equation for something that is open on one end and closed on the other. Of course, you can have like a pair of panpipes or just a regular pipe. You can have something that's open on both ends. What does that look like? Well, it looks a little different, but that is half a wavelength. And then so an antinode on both ends, half a wavelength. If you then try and go the next highest frequency, what do you get? You've got to squeeze another half a wavelength in between those. You get 2 wavelengths, and then 3, and then 4, and so on. The math of this one is identical to the math of something that's closed on both ends. It's not uncommon for standing waves to build up in solid objects. In fact, that's exactly how a tuning fork works. When you hit it, it creates lots of different frequencies. It's very chaotic to hit this against something, but when you do so, most of those things just die out very quickly. It's only the standing waves that manage to reinforce themselves and get bigger and bigger and bigger. Standing waves in solid objects, you can use one object to force another to vibrate. This is called a forced vibration. Let me give you a good example. I've got a tuning fork here. I've got a chalkboard there. That's about the only time I ever use a chalkboard anymore. You ready? The tuning fork forces the chalkboard to vibrate. You'll notice the chalkboard was a lower frequency, and that's because the tuning fork is going push, 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 but the chalkboard is vibrating slower than that. And so you end up with something where it's not being pushed every time, it's being pushed every second time or third time or fourth time, but it still allows a standing wave to build up. That is a forced vibration. You can get standing waves to build up in, say, an aluminum rod in what is the most annoying physics demo I have. And I'm sorry, it just doesn't have that same annoyance factor on a video rather than in person. So this is just an aluminum rod, and I put a little resin, the same stuff you put on violin bows, on my fingers. So we can hit this rod against a table and get a little sound, but check this out. if I just take it and stroke my fingers along it, that's known as the singing rod, and boy, is it obnoxious. So because waves are traveling energy, it's entirely possible for a wave to give something a push at a distance. And so you can have something that is vibrating with a particular sound over here, and if its vibrations are at the same frequency as another object would tend to vibrate over here, then it'll come in and it'll give it a push, and just like a swing, it'll give it a push and the thing will vibrate, and as soon as it gets back to its original position, the next compression hits and gives it another push. And then that happens over and over and over again, and this thing starts to vibrate harder and harder and harder. We call that resonance, and it only works at the natural frequency of the object. You might notice this if you're driving. If you drive a certain speed, especially if you have an older car, something in your car might start to rattle or hum. The window or the dashboard or something like that will start to vibrate. And that is because the motor is vibrating at the natural frequency of that part of your car. It's very hard to do that with something like, say, a piece of tissue paper. It changes its shape way too much to really have a natural frequency. But solid, firm objects do, and that's why you can often tell what something is, even if you can't see it. You can just hear it jingling. Like keys, for example. You can tell that they're keys, even though they're out of frame, because you know what keys sound like. So lots of objects have a natural frequency. This tuning fork has a natural frequency that is based on the fact that it is made of aluminum and it is this specific size and this specific shape. In general, larger things are going to have a higher natural frequency and smaller things will have a lower natural frequency. Also, the more dense things are, they tend to have a higher natural frequency, and the more flexible they are, the lower natural frequency they tend to have. But in any case, in order for resonance to occur, the sound, the vibration that causes it, has to be at the natural frequency or a multiple of the natural frequency of the object it's causing to resonate. So that's the end of our waves basics. In the next couple of videos, we're going to get into some of the particulars about light and sound, and then get even more into the details of lenses and mirrors, as well as some interesting optical phenomenon like what's called thin film interference. Why does a little bit of gasoline or oil on a mud puddle make it all pretty and shiny looking? See you there.